Hi, we're going to continue talking about statistical thermodynamics, and we're going to go from the Boltzmann distribution, which we just talked about, to a better understanding of what the partition function is. So this is topic B. Okay, so the partition function. And the key idea is that the partition function is an indication of the number of occupied states. So it's calculated by drawing on calculated or spectroscopically determined structural information about molecules. So if we understand the energies of molecules, we can calculate a Q, and we'll see in the next section, we can take that Q and extract out anything from enthalpy to Gibbs free energy. So that is the important thing, is the partition function Q contains all the thermodynamic information about the system, such as internal energy, entropy, heat capacities, and so on. So when we go back to the Boltzmann's distribution, this is just written out larger so I can point to each term easier. When we talk about the population of any state, I, relative to the total number of molecules, so you could call this the fraction of molecules in the ith energy state, is going to be equal to E to the minus the energy of that state divided by KT, divided by Q. And Q is now the partition function. So it's the sum of all of these possible terms. So the sum of each possible energy level in the system within that exponent. The first term is always going to be 1 because we're going to define the ground state to be 0, and then each of these energies is the energy above the 0 state. So E1 is really the energy of the second state minus the energy of the first state. So you're just looking at how far away the next energy level is. So the partition function Q gives the number of thermally accessible states at the temperature of interest. So if we look back at this picture from the last topic, at t equals 0, the partition function equals 1. As it goes up, more states are populated. When you get to t equals infinity, all states are equally populated. So if we look at that mathematically, at t equals 0, then this first term, EI, is 0, so it's e to the minus 0, so the first term is 1. So you get 1 plus, but then 1 over 0 for any of the more excited states, 1 over 0 is equal to infinity, so it's e to the minus infinity. And so at t equals 0, you get a partition function of 1. And only the ground state is populated. As you get to higher states, if t equals infinity, this partition function here, then each of these is e to the minus 0. So they're each equal to 1. So if t is infinity in the denominator, then each of these terms is e to the minus 0. And so you get 1 plus 1 plus 1. And the partition function is simply a sum of the number of states you have. So it can be any number. If you had 2 states, it would add to 2. If you have 3 states, it would add to 3. Most molecules have even more than that. So, but the important thing is each term will have the same value. Each term will be 1. Each state can be populated. Okay, so this is just written out so it's bigger so I can talk about it more easily too. The bottom of page 505 to the top of the second column. What is the significance of Q? So number 1 is Q increases with temperature. Low temperatures, Q is small and falls to the degeneracy of the ground state. So The ground state's the only one that's populated, but if you had a degenerate ground state, the partition function would be equal to the degeneracy. So if you just have one state in the ground at the lowest energy, it'd be 1. But if you had 2 states that were equal here, the partition function would end up at that degeneracy of 2. Molecules with closely spaced energy levels, like rotational states, have very large partition functions, and molecules with widely spaced energy levels can be expected to have small partition functions. So that's really because of, it's really how far above the energy. So if you're at some moderate temperature, if this is a huge number, this is going to be a small number, e to the minus big number. And so it's really how far apart the energy levels are when you're at moderate temperatures that will determine how many possible states can be populated. So self-test. Self-test 12B.1. You can just write out the partition function. The degeneracy of the ground state is 4. And so 4 times e to the minus 0 is 4, plus 2 for the degeneracy of the next excited state. And then it's e to the minus energy of that relative to the ground state. And it just gives you all of the numbers there. So you could make a graph that looks exactly like that one. But to see that in this case where you have 4 plus 2 total states, the degeneracy of the ground state and the degeneracy of the first excited state, your partition function is going to range from 4 when you only have that ground state populated up to 6 at higher temperatures when you have all 6 of them populated. So how do we actually calculate a partition function? So the translational partition function is a good one to look at to start with. So if you think about it, translational energy levels are super close together. So trying to do a sum, an infinite sum of closely spaced energy levels would be really hard mathematically. So what we'll do instead, well, let's start by thinking about how we can even talk about them separately. So if you're talking about a partition function, you have e to the minus the energy of each state and the energy of each molecule. So each molecule could be I or J. And then you can have different modes of energy. So this could be rotational and this could be vibrational. So if you write that in, then the total energy is the energy of rotation and vibration. I think I said it in those order. But when you look at the math of that, e to the x plus y is equal to e to the x times e to the y. And so you can take what's a sum in the exponent, and that allows you to pull those two apart, and you can say that it's the partition function for one mode times the partition function of the second mode. So x and y are equal to a and b. And so a partition function for a molecule can be separated, and you can calculate the contribution from translational, rotational, vibrational, and electronic energy states. So when we do that, we're going to start with translational, and an infinite sum, which is what we have to do, is pretty much impossible mathematically when you have so many energy states. So what we're going to use is the particle in the box energy. So let's say we have a one-dimensional particle in a box, and we want to calculate the Q for translation. The energies are the quantum number in the x direction squared, Planck's constant squared over 8m, the length of the box squared. And that just comes straight out of our chapter on quantum mechanics when we looked at translational energies. So we're going to set the lowest energy equal to 0. And so when we have the lowest energy, it's when this is equal to 1. So the energy would be h squared over 8m, length of the box squared. And we call that what are we calling that? EX. Then we're going to subtract that from each energy. So that would mean in the ground state, 1 minus 1, the energy is 0. In the second excited state, it's 2 squared minus 1. would give you 3 times EX. So essentially, we're setting our reference point to be 0 when this ground state is our first term. So what we have to do is take an infinite sum then from nx equals 1 all the way up to infinity. But the translational states are so close together, we're going to assume that we can say it's an integral, that we can integrate rather than take a sum. That really just says that they're so close together, we don't have to worry about the space in between. And rather than integrating from 1 to infinity, doesn't change it too much. It's approximately true that the sum is equal to the integral, and that the integral can be changed to 0 to infinity instead of 1 to infinity. That'll just make the math of this integral a lot easier. So then this will be the integral you're doing. So we're taking an integral where this is the energy. So I'll put it in here. And the other thing that we did, because this should really be nx squared minus 1. Well, as nx gets bigger, subtracting the 1 doesn't change it very much. So that's another approximation here. So replacing nx squared minus 1 with just nx squared, this integral will be easier to do. And this would be the integral. So one-dimensional particle in a box, you could split that and you could do the partition function for each dimension, x, y, and z. And then if you have a particle in a beaker, a 3-dimensional box, you just have to take the product of all 3 of those. So this term out front becomes 3/2 instead of 1/2 if you multiply them by each other, and then length of the box in all 3 directions. So the big thing is to think about in each case, what approximations do we make in order to say this is the partition function for translational energy? They were changing the integral from 1, or first changing the summation to an integral, and then changing our limits from 1 to infinity to 0 to infinity, and then saying that nx squared minus 1 is the same as nx squared. All of that makes the integral easier, and that's the equation we'll use. Very rarely would that ever lead to any issues, those approximations. So, then we can look at the rotational partition function. And this, so what we just went through for translational is on page 507 if you want to look back through that more carefully. I just set it up. They actually show you how to do the integral. Then when we look at rotational partition function, here's the final form, equation 5. It's very similar. Rotational energies are pretty close together if you're at normal temperatures. And so this justification shows you that it's almost exactly the same. We can replace the summation with an integral. We can, yeah, I didn't write any of that on here. We can replace the summation with an integral, and then we have to take into account the degeneracy because rotational states are degenerate. And so that's what the 2j plus 1 is. That's basically the GL, the degeneracy of that level. And then we put the energies in that we know from the rigid rotor back in the quantum mechanics section, and we integrate over J. So the rest of that justification just shows you how you can do that mathematically. And what you end up with is the rotational partition function is Boltzmann's constant times temperature divided by the symmetry times Planck's constant times the rotational constant for whatever molecule you're talking about. And I'll always give you the symmetry number because we haven't talked much about it, but it really has to do with how many different ways you can rotate a molecule and have it look the same. So we have a nice rotational partition function, same approximation that the summation could be replaced by an integral. Then the vibrational one, surprisingly, mathematically, you don't have to make any approximations. So if you look at a harmonic oscillator, then the vibrational partition function will end up being this right here, where this is Planck's constant times the fundamental frequency of the vibration divided by kT. And so E0 we set to be 0, Then the first excited state goes up by h nu, second excited state 2h nu. And what you end up with is Q is equal to 1 plus e to the x plus e to the x squared plus x squared. So if we call this x, and then this would be x squared, because if you square this, you get a 2 there, plus x cubed. So it's an infinite sum, but you can see mathematically that that infinite sum is really just equal to 1 over 1 minus x. And you do that by going up here, and we start with the infinite sum, and if we multiply it by 1 minus x, then what do you get? You get 1 plus x, so you get, you get 1 times all of this, and then you get subtracted from that x times all of this. So minus x times 1 is minus x squared when you multiply. So when you multiply 1 by all of this, you get the infinite sum. And then when you multiply minus x times all of it, you get this right here, minus x. So minus x times 1, minus x times x, minus x times x squared. And if you look at that, that's just equal to 1, because you're subtracting off each of these terms. So the infinite sum times 1 minus x equals 1. So you can take that over to this side. And so your infinite sum is equal to 1 over 1 minus x. And so the vibrational partition function, and the only approximation we're making is that it's a harmonic oscillator. But mathematically, we didn't have to say anything about an infinite sum. So it's going to be equal to 1 over 1 minus our x was just e to the minus h nu over kt. And so that will be an exact expression if it's a harmonic oscillator. So go ahead and take a break. Yeah, I didn't do that one. So go ahead and take a break and evaluate the populations of the NJ of the first 3 vibrational states in a sample containing N molecules. So you'll yeah. So stop and do this one. And you'll just be using this equation right here. Okay, so the very last partition function that we need to deal with is the electronic. And at normal temperatures, pretty much the only populated state for electronic energy is the ground state. The other levels are so far away that they won't be populated. So unless you're at high temperature, this will always be true. And that's just saying that the only one that has any significant contribution is that ground state. So it's about equal to the degeneracy of the ground state. So if your ground state has a degeneracy of 4 times e to the 0 equals 1, this term generally will be 0 as you go up. Let's just look at this one where it's not equal to 0. So this is self-test 12b. 0.5, a certain atom has a 4-fold degenerate ground state and a 6-fold degenerate excited state that's 400 reciprocal centimeters above the ground state. Calculate its electronic partition function at 25 degrees. So these states are not so far apart. So this is one where this wouldn't necessarily be true because this energy is relatively close. So 4 times e to the minus 0, and then 6 times e to the minus, and we just have to put the energy in. So it tells us that it's 400 reciprocal centimeters above the ground state. So Planck's constant times the speed of light. If you put it in centimeters, you can just put in the frequency in reciprocal centimeters divided by Boltzmann's constant times temperature is 1.93. And so you get an electronic partition function that's a little bit more than the degeneracy of the ground state, but not too much, 4.87. So 4.87 states are populated at 25 degrees. So we'll go on and think about the significance when we continue into the next section where we calculate the bulk properties. So we're going to look at calculating the internal energy, heat capacity, and things. We can do that all from just knowing what are the vibrational frequencies, what are the rotational constants, what are the electronic energies, and from that we can extract out the information about a bulk system. So that is all we'll do about the partition function.